Hello everyone. In this video, let me give a brief lecture about limit, continuity and differentiability concepts. It's from calculus main topic. In GATE examination, totally 17 branches has the engineering mathematics syllabus. 17 branches also has the calculus main topic and also has the subtopic limit, continuity and differentiability. In this video, I will give only summary of limit, continuity and differentiability concept. In the forthcoming videos, let me solve the previous year GATE questions related to this concept. This video is very useful for all branches, 17 branches, AE to XE, Aerospace Engineering to Engineering Sciences. First, I give the weightage of this topic. In GATE examination, maximum 3 marks comes from calculus topic. Maximum 3 marks comes from calculus topics. Moreover, 40% of chances to get a question from this subtopic. 40% of chances to get a question from limit, continuity and differentiability subtopic. So it is very important topic and interesting topic. Now let's move on to the concept. First, what is limit? First I explain the limit of the function, definition of limit. Suppose f of x is defined when x is near the number a, then we write limit extends to a, f of x equal to L. This means that f is defined on some open interval that contains a except possibly at a itself. Then we write limit extends to a, f of x equal to L. And how to say the limit of f of x as x approaches a equals L. That means if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a but not equal to a. It is very important. X to be sufficiently close to a but not equal to a. This is the definition of limit of the function. Next, I will give an example. Guess the value of limit extends to 1, x minus 1 by x square minus 1. Listen that the function f of x equal to x minus 1 by x square minus 1 is not defined. The function f of x is not defined when x equal to 1. But that doesn't matter because the definition of limit says that we consider values of x that are close to 1 but not equal to 1. So it doesn't matter. Okay, the function f of x is not defined when x equal to 1, but that doesn't matter because the definition of limit says that we consider the value of x that are close to 1 but not equal to 1. Now come to the table. The table gives the values of f of x for the values of x that approaches 1 but not equal to 1. That close to 1 but not equal to 1. The first table gives the x less than 1 values, 0.9, 0.99, we can put 0.9, we can get 0.5263, etc. And the second table gives the x greater than 1 values. All the values nearest to 0.5. So by using the values in the table, we guess limit extends to 1, x minus 1 by x square minus 1 equal to 0.5. This is the definition of limit of the function and one example. Okay. Next I am going to explain one-sided limit. What is one-sided limit? Here I am going to explain one function. The Heaviside function h is defined by h of t equal to 0 if t less than 0, 1 if t greater than or equal to 0. The diagram is here. H of t equal to 0 if t less than 0. T is less than 0, then h of t equal to 0. This is h of t. Okay. Next, if t greater than or equal to 0, all the values of h of t is 1. So this is the diagram of the Heaviside function. Here limit t tends to 0 minus h of t equal to 0 and limit t tends to 0 plus h of t equal to 1. This is what is 0 minus and 0 plus. I am going to explain. As t approaches 0 from the left, t approaches 0 from the left, h of t approaches 0. As t approaches 0 from the right, h of t approaches 1. So we write limit t tends to 0 minus h of t equal to 0 and limit t tends to 0 plus h of t equal to 1. t tends to 0 minus means left hand side limit of h of t as t approaches 0. T tends to 0 plus means right hand limit of h of t as t approaches 0. Here there is no single number, that means these two are not equal, that h of t approaches 0 as t approaches 0. Limit t tends to 0, h of t does not exist. Does not exist. Because here left hand limit and right hand limit are not equal. This is the one-sided limit function, Heaviside function. Here left hand limit and right hand limit not equal. So limit t tends to 0, h of t does not exist. Next, one result. I am going to explain one result. Limit extends to a f of x equal to L if and only if limit extends to a minus f of x equal to L and limit extends to a plus f of x equal to L. A minus means left hand limit, a plus means right hand limit. Left hand limit and right hand limit equal, then only limit extends to a f of x equal to L. The result says this one. Left hand limit and right hand limit equal, then only limit extends to a f of x equal to L. Now I give the example of one example of this result. Okay, here limit extends to 0, modulus x equal to 0. I am going to explain what is this. Limit extends to 0, modulus x equal to 0. What is the definition of modulus x function? How to define modulus x function? Modulus x equal to x if x greater than or equal to 0 and modulus x equal to minus x if x less than 0. This is the diagram of modulus x function. X is greater than 0, then modulus x is x. This is the x is greater than 0 values. This is also x is less than 0 values. This is x is less than 0 values. Suppose you put x value is minus 1, minus of minus 1 is plus 1. Y is also positive. Modulus x function is always positive. So this is the diagram of modulus x function. Here, since modulus x equal to x, for x greater than 0, we have modulus x equal to x. For x greater than 0, we have limit x tends to 0 plus modulus x equal to limit x tends to 0 plus x. This is also 0. Put x equal to 0. So the right hand limit of modulus x function as x approaches to 0 is 0. Similarly, for x less than 0, that means modulus x equal to minus x, then limit x tends to 0, 0 minus is, this is not plus, minus, left hand limit. Modulus x equal to limit x tends to 0 minus, this is minus x, this is also 0. By using that limit, that result, right hand limit and left hand limit equal to 0. So limit x tends to 0, modulus x equal to 0 by using that result. Because here right hand limit and left hand limit equal, so limit x tends to 0, modulus x equal to 0. Next, I give another one example. This example mention the result does not exist. Okay, I will give another one example. The result does not satisfy. Limit x tends to 0, modulus x by x does not exist. How to explain? This is the diagram of this function, modulus x by x. Suppose modulus x, how to define modulus x function? I already defined modulus x equal to x. If x greater than or equal to 0, minus x if x is less than 0. Put x equal to positive value, we can get positive 1. Okay. Next, put x equal to negative values, we can get negative values. Negative minus 1, minus 1. Okay, negative of 1 value. Okay, that means limit x tends to 0 plus modulus x by x equal to limit x tends to 0 plus modulus x is x by x, this is equal to 1. But you have to take left hand limit modulus x by x equal to limit x tends to 0 minus modulus x is minus x by x equal to minus 1. Here these two values are not equal. Left hand limit is not equal to right hand limit. In this case the limit does not exist. Limit x tends to 0 modulus x by x does not exist because this function does not satisfy that result. That result is left hand limit not equal to right hand limit, then limit x tends to 0 modulus x by x does not exist. Does not exist. Next is, what is next? What is infinite limit? Let f be a function defined on both sides of a except possibly at a itself, then limit x tends to a f of x equal to infinity. That means that the value of f of x can be made arbitrarily large. Can be made arbitrarily large means f of x, the value of f of x becomes infinity by taking x sufficiently close to a but not equal to a. So this is called infinite limits. Once again I explain, this means that the value of f of x can be made arbitrarily large by taking x sufficiently close to a but not equal to a. This does not mean that infinity as a number. This does not mean that infinity as a number. That is, it doesn't mean that limit exists. It simply say limit does not exist. We symbolically write limit extends to f of x equal to infinity. We simply say the limit does not exist. It means the limit does not exist. One example, I will give an example. Find limit extends to 0, 1 by x square if it exists. This is the diagram of 1 by x square, y equal to 1 by x square function. We can put the positive values, we can get this curve, and the negative values, we can get this curve. Okay, here x becomes close to 0, x becomes close to 0, x square also becomes close to 0. X becomes close to 0 means x square also becomes close to 0. But 1 by x square becomes very large, infinity. 1 by 0, 1 by x square becomes very large. We can say by using that diagram, the values of f of x can be made arbitrarily large by taking x close to 0. So limit extends to 0, 1 by x square equal to infinity. That means limit extends to 0, 1 by x square does not exist. Does not exist. Next, one definition. This is arbitrarily negative infinite limit. That means the values of f of x can be made arbitrarily large negative by taking x sufficiently close to a but not equal to a. In that case, limit extends to a f of x equal to minus infinity. In that case also say limit exists. Next, let us discuss what is vertical asymptote. The line x equal to a is called the vertical asymptote of the curve y equal to f of x if at least one of the following statement is true. Limit extends to a f of x equal to infinity or minus infinity, and limit extends to a minus f of x equal to infinity or minus infinity. A minus means left hand limit at a, and limit extends to a plus f of x equal to infinity or minus infinity. That means right hand limit at a. The line satisfies at least one of these statements, then the line x equal to a is called the vertical asymptote of that curve y equal to f of x. Next, let us discuss the example of how to find the vertical asymptote of one curve. Find the vertical asymptote of curve f of x equal to tan x. Here I draw the curve of tan x. Tan 0, 0 and tan 45 is 1 and tan pi by 2 is infinity. This is the diagram of tan x curve. Here limit x tends to pi by 2 minus x tends to pi by 2 minus tan x equal to plus infinity. Limit x tends to pi by 2 minus tan x equal to plus infinity. Pi by 2 minus means left hand limit at pi by 2. Left hand limit at pi by 2. That value is plus infinity. That means as x approaches pi by 2, from the left, x approaches pi by 2, from the left, the value of f of x approaches infinity. So the left hand limit at pi by 2 is plus infinity. Similarly, limit extends to pi by 2 plus, limit extends to pi by 2 plus tan x equal to minus infinity. Right hand limit is minus infinity. That is, as x approaches pi by 2, from the right, the value of f of x, tan x, the value of tan x approaches minus infinity, Here tan x curve satisfies these two conditions. Limit extends to pi by 2 minus f of x equal to plus infinity, and limit extends to pi by 2 plus f of x equal to minus infinity. This shows that the line x equal to pi by 2 is a vertical asymptote. Similarly, we can prove that the line x equal to 3 pi by 2 also vertical asymptote. So the lines x equal to 2n plus 1 pi by 2, where n is an integer, the lines are all vertical asymptote of tan x. This is the one example of how to find the vertical asymptotes. Next, limit laws. Next, I am going to explain some limit laws. Suppose that c is a constant and the limit extends to a f of x and limit extends to a g of x exist, then the first condition, the first law is the limit of the sum is the sum of the limits. That means limit extends to a f of x plus g of x equal to limit extends to a f of x plus limit extends to a g of x. That means the limit of the sum is the sum of the limits. This is the first law. Second one is the limit of the difference is the difference of the limits. Third one is the limit of a constant time function. Constant time function is the constant times the limit of the function. This is the third law. Fourth law is the limit of the product. Limit of the product is the product of the limits. Next, fifth one is the limit of the quotient is the quotient of the limits, provided the limit of the denominator is not equal to 0, then only the quotient exists. Okay, for sixth one is limit extends to a f of x whole power n equal to limit extends to a f of x whole power n. This is the sixth one. Seventh one is the constant limit at x equal to a, any limit we can get the constant value, and limit extends to a x is a, limit extends to a x power n, a power n, and limit extends to a square root 10 nth root of x equal to nth root of a, and limit extends to a nth root of f of x equal to nth root of limit extends to a f of x. This is the n is a positive integer. These are the limit laws. Next, I am going to explain one property, direct substitution property. That is, if f is a polynomial or rational function and a is the domain of f, then limit extends to a f of x equal to f of a. This is the one law. If f is a polynomial or a rational function and a is the domain of f, then limit extends to a f of x equal to f of a. Next one is one result, that is, if f of x equal to g of x when x not equal to a, then limit extends to a f of x equal to limit extends to a g of x, provided the limit exists. Suppose the limit exists and f and g are equal function, then the limit extends to a f of x are also equal. Limit extends to a f of x equal to limit extends to a g of x. Next one is the precise definition of a limit, that is mathematical definition of a limit. Let f be a function defined on f be a function defined on some open interval that contains the number a except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write limit extends to a f of x equal to L. If for every number epsilon greater than 0, there is a number delta greater than 0 such that if 0 less than modulus x minus a less than delta, then modulus f of x minus L less than epsilon. That means since modulus x minus a is the distance from x to a, modulus x minus a is the distance from x to a, and modulus f of x minus L is the distance from f of x to L, and epsilon can be arbitrarily small, the definition of a limit means that the distance between f of x and L can be made arbitrarily small by taking the distance from x to a sufficiently small but not 0. This is the definition of mathematical definition of a limit. Friends, this is the part 1 video of limit, continuity and differentiability concept. Limit, continuity and differentiability concept will continue in the part 2 video also. Thank you for watching. See you in the part 2 video. Thank you. If you like this video, please like, share and subscribe my channel to encourage me. Thank you.